Well, good morning, everyone. This is Steve Case from Electro Rent, and welcome to our second in the series of the Fast and Furious. And we're going to be talking to Tektronix this morning about PCI Express 6 and some challenges. And so everybody's online, and welcome to our presenters. We have this morning Joey Chu from Tektronix. He's a PCIe applications engineer and programmer, so he's got some insights into how a lot of the software works inside of the applications. And we also have David Baus here, and he'll be standing by to answer questions. So we can get pretty technical here. David's also part of the PCIe community and working on the standards with all the guys at Tektronix. And before we get started, I was going to say we have a little commercial for Electro Rent. We have about $1.2 billion of inventory across the world. And we also have the equipment we're talking about today. We have the DPS 70,000 series scope from Tektronix. We currently have one on the shelf, in fact. But we can provide the equipment all over the world, whether it's in the UK, China, or other parts of the world. So no matter where you are, we can support you. And I'd just like to say good morning to our guests, Joey Chu and David Baus. Good morning, gentlemen.
Morning, Steve.
Good morning.
So during the, we're going to take about 30 minutes to go through some slides that Joey will do, and I'll make you presenter now, Joey. And in that 30 minutes, we'll hold the questions off to the end, but you can stage them in the questions section of the webinar. And then during the end of it, we're going to actually have a survey to see some interesting facts. So go, Joey. I will make you the presenter.
All right. Thank you, Steve. Hello, everyone. My name is Joey Chu, PCIe Applications Engineer with Tektronix. Thank you for joining today for the discussion of what's new in PCI Express 6.0 and physical layer testing challenges. So here's our agenda for today. We'll first take a look at the PCI Express 6.0 spec updates. We are excited to see the release of PCI Express 6.0 base spec Ref 1.0 being released. And then we'll also talk about the PCI evolution over the years. Next, we'll take a look at the 6.0, the 64 gigatransfer per second base TX measurements. We'll take a deeper look at some of the critical test items and the newly introduced test items. And then we'll take a look at the 100 meg Refclk, which becomes more and more important and challenging in starting Gen 5, given the tightening of the requirements of Jitter. And finally, we'll take a look at the receiver calibration for Gen 6 PAM4 and also some receiver tests. So let's first take a look at the 6.0 spec updates. So the PCI 6.0 debuts 2022 during the 5G critical mass, where the needs for more server nodes, high bandwidth network, and also the high performance computing and the AI applications. And there are a few key features from the PCIe architecture that makes it suitable for that application. So let's take a look at the figure on the top bottom right. There are increased bandwidth with low latency as one of the key features enabling these applications, and also the backwards compatibility. And we're seeing that PCI is accelerating relatively fast. We see on the bottom left, there's the evolution of each generation of PCIe, and a line that indicates the I/O bandwidth doubles every 3 years. We see that the PCIe evolved with the trajectory of that doubling of the bandwidth every 3 years. And we see that the PCIe 6.0 now has a 64 giga transfer per second, which is a link bandwidth of 66 gigabits per second. And with a bi-16 bidirectional lane, it has a lane bandwidth of 256 gigabytes per second. So let's take a look at what the PCIe 6.0 spec snapshot of as of today. So we've seen that the base spec Ref 1.0 has been released. That's the first spec describing the chip level behavior on all levels of the stack. And then trailing not far behind, we're seeing that the CAM spec, CAM stands for car electromechanical, as one of the most popular form factor of PCIe. The CAM spec is being developed and with a 0.5 ref that's defined in at the system level and the adding car level. For the more detailed electrical compliance tests, we have the PCIe 6.0 physical layer test spec. It's also Ref 0.5 that's under development, but we have some preliminary guideline that we can refer to with regard to the transmitter, the receiver link EQ, and the PL bandwidth tests. So here's a detailed overview of key parameters from PCIe 4.0, 5.0 to 6.0. So the data rate has moved from 16 giga transfer per second for 4.0 to 32 gig for 5, and now we are at 64 giga transfer per second, and which is the new modulation signaling scheme that applies a multi-level PAM4 modulation. And we also see that the channel loss defined for 4.0 was that 27 to 30 dB loss at the Nyquist frequency of 8 gig. To 5.0, that is 34 to 37 dB at 16 gig. For 6.0, it's now at 30 to 33 dB, also at the 16 gig, given that the 6.0 is with the same Nyquist, but different kind of signaling method comparing to PCIe 5. And we see a expansion on the reference CTLE and DFE. The CTLE has become more complex, more poles and zeros, and also increased range of the DC gain. the behavioral DFE also adding more taps. Now we're at 16 taps for PCIe 6. The eye width and eye height has also been redefined, and now as PAM4, we have 3 eyes. So the spec defines the top eye, assuming that we have symmetry from top eye and the bottom eye, and also the top eye takes more impairments comparing to the middle eye. So now we are at 3.125 picosecond in eye width and 6 millivolt in eye height. Also, we can see on Refclk jitter limits that the Refclk jitter limits has been tightened from 500 femtosecond for PCIe 4 to 150 femtosecond for PCIe 5, and then now it has to be within 100 femtosecond. And the scope bandwidth is the same for PCIe 5, given the same nyquist frequency. So we're also looking at the 50 gig scope bandwidth for PCIe Gen 6. Next, let's take a look at the 64 gig transfer per second base TX measurements. Here's the list of the base transmitter measurement. And highlighted here, we have SNDR, transmitter equalization, and ratio level mismatch. These are some of the key parameters that's either newly introduced or have some certain revision that we want to take a deeper dive on these test items. So let's first take a look at the SNDR. SNDR is we see that SNDR defined in IEEE, but there's slightly different definition in PCIe comparing from the IEEE. And there's another term that's called SNR. It's quite similar to this, but there's one important term here that makes it different from the SNR. That's the sigma E here. So we can take a look at the equation on the top left. The SNDR is defined as this equation. So what we'll do is that we capture the waveform, and then we'll get a linear fit pulse response of the waveform. With that, we get the Pmax, which is a signal power, and sigma n. It's a standard deviation of the noise. And the sigma E is one important term here that represents the nonlinear, non-compensatable distortion here. And the measurement methodology is that we will use the linear fit pulse response to reconstruct the waveform, and then compare to the original average waveform. Any difference between the two will be contributed to this sigma E, which is a nonlinear term in this equation. And here's the detail on the SNDR measurement requirements. We will be using the Gen 6 compliance pattern. We do want to consider SSC for the SRIS. This is one of the Refclk architecture that we'll be talking later on. And the TX equalization will be Q0, which is no equalization. The real-time scope waveform capture requires a bandwidth of 50 gig, record length of minimum of 250 pattern repetitions, and also we'll be applying the fourth order Bessel-Thompson filter, which has a 3 dB roll-off at 33 gigahertz. The SIGMA-E requires the pulse length of 600 UI post delay, and also we want to do resampling to make sure that each UI there's 32 points per UI. And also we are looking at the PRBS portion of the compliance pattern only. That's one of the key difference comparing to the SNDR defined in IEEE. So the SNDR in IEEE defines that takes the all pattern for the SNDR measurement. Also, we want a clock recovery to be applied, and this is one of the challenges given the DSP implementation is not explicitly defined in the spec. And for the noise turn sigma n, we will take the 64 run, which is the low frequency portion of the compliance pattern, for each PAM4 level considered. It will do 8 evenly spaced points within that average voltage level. And we did SNDR measurement feasibility study last year. This is to we want to make sure that the measurement system is capable of doing this measurement with the potential needs that's defined in the spec for a potential 15 dB lossy channel. So here we use the Anritsu MP1900A BERT as a source of the 32 gigabaud PAM4 signal. We add a variable ISI board that accounts for the channel loss. We experiment the channel loss of 1.5 dB, 7.43 dB, 10.79, and then 14.33 dB from that variable ISI channel. And then we connect the signal to the Tektronix 70K SX scope, that is a 70 gig scope model. We do want to confirm that the SSC is on and off. So we have data having SSC. So the result turns out that the SNDR will be slightly degraded with the ISI channel, but not much through that 14 dB channel. We can see that it's just 1 dB difference. Also, the result between SSC on and off is pretty close, so that we have confidence that the measurement system is capable of measure this PCIe Gen 6 SNDR. Moving on, let's take a look at the transmitter equalization, which adds the expansion of the second precursor that is newly added in Gen 6. With that, we also have the presets redefined for PCIe Gen 5. It was P0 to P10. Now, because of the multi-level, now we have Q0 to Q10. And there are a couple of things to highlight that it's the second precursor, we have a heavier precursor weighting. And also we have new sort of optimal preset for receiver calibration that is highlighted in this. It's usually Q5, Q8, and Q9. Also, one more thing to note is that the measurement method for transmitter equalization has been updated. It's a new method called AC Fit Method. It will measure through the step response, capturing both the equalized waveform and the non-equalized waveform. And we will apply cursors on the non-equalized step response, trying to minimize the mean square error. Here we have an example of how that works. Know that this AC Fit method has been introduced during the Gen 5. So for this example, we are looking at the P4 and P9, that is from Gen 5. But we believe that the same method will be carried on for Gen 6, given it's the same methodology. So what happened is that we see on the left, there's a blue line indicate the step response of P4, which is without any equalization. And we have a step response of P9 that is with the equalizations. The step response is captured using the compliance pattern with that long run length. And we capture with all presets. And then we'll compare each of the equalized waveform with the P4, which is no equalization. We apply the FAR filter and adjust the precursor and post-cursor, all the cursors, through a iterative process to minimize the mean square errors of each preset so that we get that cursor values. That's how the AC Fit method works. Moving on to the transmitter ratio level mismatch. This is also a newly introduced items. We've seen this in IEEE as well, but there's a slightly different between the definition from IEEE and PCIe. Let's first take a look at how this measurement works. So we can see on the left, there's a RLM equation. We have 4 levels of the PAM4 signal. We want to take the V-mid, which is the highest level, and the lowest level, and get an average of the two. And then we have intermediate level, that is ES1 and ES2, that is account for the delta between the lower 2 level comparing to V-mid and the higher 2 level comparing to V-mid. And the expression of RLM is that we want to have a RLM of 100% that indicates a perfectly balanced level ratio. So on the right, we have an example of an ideal case. We have a voltage swing of 800 millivolts and V3 400, V2 133, and V-mid at 0, and V1 at minus 133, and V0 at minus 400. In this case, we compute that the ES1 is that about 1/3, ES2 is also about 1/3. So in this case, we calculate the RLM as 100%, which is one. That is the ideal RLM results. And let's take a look at the non-ideal case of RLM. In this case, we also have a same voltage swing of 800, but now V3 at 430, V2 at 160, V-mid at 10, V1 at minus 100, and V0 at minus 370. In this case, we have ES1 at 0.29, ES2 at 0.36. And in this case, the RLM is calculated as 0.92, which is the spec defines 0.95 spec limits. Here's an overview of Tektronix PCIe Gen 5 base solution. So on the right, we have the DPO 70K SX, that is a 70 gig scope platform, real-time scope. And there's a lot of pieces on the left as software that makes the whole solution. So on the top left, we have a PAM4 analysis application. That is the application of measuring the PAM4 signal. That's the there's an algorithm that enables the SNDR measurement, the RLM measurements. Also, we have SDOA. That's a serial data link analysis. We can do embed, and which is especially useful in the case for base measurement, where we will kind of wanted to embed our own patch loss in the computation. Also, we have DPO Jet, that is a well-known analysis tool for NRZ. That is also able to take measurement of the channel-to-channel skew. So with that, all the analysis tool, we have that the TechExpress automation software that is now supporting the PCIe Gen 6 base spec. It's a automation software that is capable of doing controlling of the device to toggle the pattern to the corresponding pattern with specific test items, and also setting the compliance test items and generating a compliance report from a single button click. So that concludes the our PCIe Gen 6 base transmitter solution and the measurement for today. Moving on, let's take a look at the 100 meg Refclk. The Refclk architecture, there's 3 Refclk architecture for the PCIe Gen 6. We have common clock architecture, which is widely used for the CAM form factor. That is a single Refclk distributed to both TX and RX. In this case, majority of the SSC jitter will be tracked by the PLLs. And we have independent Refclk called separate clock no SSC and separate clock independent SSC. That's basically SSC turning on or not. In this case, the jitter at the RX will not, the SSC jitter will not be tracked, so that the jitter characteristic will be a lot tighter. Also, we have data clock. There's no Refclk on the receiver side, so we'll just do the, depends on the our receiver CDR to take the clock from the data. Here's an example of how the Refclk jitter measurement works. We, on the top left, we have the transfer function of the Refclk scenario of the common clock. And we'll apply the PLL number 1 and number 2, which is corresponding to the TX PLL and the RX PLL. And what we're looking for is on the bottom right. That's the high frequency jitter plot of a raw waveform, and also the jitter plot that is after the PLL and CDR filters being applied. And what we are looking for Gen 6 is that the jitter amount needs to be within 0.1 picosecond or 100 femtosecond RMS number. Next, let's take a look at the PAM4 receiver calibration and the test. So we talked about the receiver equalization expansion. The CTLE has now, with the 6 poles and 3 zeros, and the DC gain of -5 to -15 with 1 dB step. DFE has been added for 16 taps now. And there's a DFE tap constraint defined spec with the empirical formula to minimize the burst errors. There's numerous receiver challenges at PCIe 6.0 64 data transfer per second and PAM4 signal. Number 1 is that we need accurate and repeatable stress-eye calibration at 32 gigabaud. And there's added validation effort to include backward compatibility for NRZ rate. So we want to make sure that it's backward compatible. And for 32 gigabaud PAM4, we're at the point that instrument noise is now cannot be ignored. So we want to accurately characterize noise and then compensate it on some of the key test items. And jitter tolerance and the BER receiver testing needs to be tested in the presence of SSC. And there's a limited post-processing tool to support that 64 gigatransfer per second PAM4 signal. That's one of the challenges, that there's no industry standard for do the analysis of this signal. Also, we want to capturing the realistic crosstalk impact with a single lane test. And also the BERT error detector equalization needs to now support up to potentially a 28 dB insertion loss that is allowed for from the DUT transmitter path. Here's a PAM4 stress-eye calibration. We want to illustrate how the test point defined, and although with the complexity of the receiver cal, we are nowadays most depends on the automation software. But as an engineer, we still wanted to kind of have a basic understanding of what is happening within the automated software. So on the left box, we have everything inside the Anritsu MP1900A BERT. It's capable of generating 32 gigabaud PAM4 signal with random jitter, sinusoidal jitter, and the differential interference that is account for the crosstalk turn, and the common mode interference added for the output signal, and that's TP1. TP3, it's after a 1 meter cable connected. So now we are calibrated at TP3, and then that's served for the short channel, and we'll also calibrate TP2 that is the long channel after the calibration channel and the replica channel being added in the system. And that will be connected to the calibration point will be connected to the DPS 70K SX scope to capture the waveform and do the post analysis. And also we have TP2P, that is after the post processing tools. We want to target a 6 millivolt I height and a 3.125 picoseconds I width at e to the minus 6 bit error rate. Here's the update for TP3 calibration. We know that the TX equalization has been expanded. So given that the TP3 calibration include the voltage swing, AC/DC balance, as well as the TX equalization and random jitter and sinusoidal jitter. One thing to note is that the cable that is connected from TP1 to TP3 is excluded from the total channel. So we calibrate at TP3 as a reference plane. For TP2, we want to calibrate the DMI, the crosstalk turn at 2.1 gigahertz from 5 to 25 millivolts. And one of the challenges that with the base spec, we are using CSIM to take the measurement. And the CSIM injects the DMI at TP2P. However, with the physical link of the calibration of BERT, we are calibrating the TP2 plane. That's without the post-processing tools that we just mentioned. So there's a conversion factor is required. So on the bottom, we see a conversion table that is dependent on which CTL we selected, and if we are calibrating for a root complex or a non-root complex, there's a conversion needs to be added in the calibration. And here we have a PAM4 stress-eye calibration example. We are using the Gen 5 base Ref3 fixtures, given the same Nyquist frequency. We use a source of PAM4 PPG and the Tektronix real-time scope. We use a post-processing tool of CSIM version 1.0.6. And with that, we close the Gen 6 root complex calibration with the methodology we just mentioned, that we close the calibration with channel loss of 33.1 dB and optimal preset of Q8, RJ at 250 femtosecond, SJ at 1.7 picoseconds, and DMI at 4.8 millivolt. Last but not least, we'd like to take a look at the receiver test. So the receiver test is commonly used with the jitter tolerance test. For jitter tolerance, we use the modified compliance pattern. It's a slightly stress pattern added compared to the compliance pattern. We want to disable the SSC on the data signal, and given that we will independently sweep the 33 kilohertz tone that is account for the SSC independently. And also we have a jitter tolerance mask from 400K to 100 meg. We want to target a FBR target of e to the minus 6 and that is without counting for the burst errors, because for Gen 6 we are adding the FEC for error correction on the system. All right, so that concludes today's presentation. We'll have a demo of the Tech Express just to kind of illustrate how that works with the latest Gen 6 test items. So here, as we move on to the screen of the, let's first take a look at the Tech Express PCI. Tech Express PCIe. We have a, so first we have a release of Gen 6 supporting the base spec. Once we have a DUT panel configured, that we know what is the generation want to test, what's the type of the device, we can move on to the test selection, and then all the test items according to the generation and type of the device will be loaded. And we can also individually enable or disable independent test items, either on signal test or preset test. And then we want to make sure the connection from the signal to the scope is set here. Once we have these configured, we can hit start. And then we'll see that the automation software configures the scope, also the BERT, and then it's asking for a connection diagram for the user to follow the expected wiring of the connection. And also a Tech Express will pop up message to indicate user to toggle to require test patterns per the spec. So while we let Tech Express run, there's a couple useful tips that I wanted to highlight. First one is in the case that we want to add additional the embed of the channels, we can do it through a filter file edit here. And the second one is that Tech Express allows user to run acquisition and analysis separately. This is especially useful if we want to test like multiple lanes and we have limited time sit in front of the scope to make the connections. We can just select scope to acquire signals for each lane and then save the waveforms for offline analysis later on. So that concludes the demo. And today's presentation.
Well, thank you so much, Joey. It's very complicated getting into the PCIe Gen 6 and with all the PAM4 complications. So just to let everybody know where we're at with the webinar, I've added a handout of all the slides in the handout section. But before we take some questions, I'm going to launch a poll here for all of us to answer. So stand by. We'll think about your questions and get ready to put them in the questions section if you have some. It would be great because we have both David and Joey here to answer them. But let's take a quick poll just to see where everybody's at. And go ahead and answer that, and then we'll just kind of give you a couple of seconds to give us an answer, and just helps us out a little bit and see where everybody's challenges are. And then votes are coming in. All right, I think that's enough for now, and hopefully people have thought of some questions. I'm going to close the poll, and thank you for doing that. The answer was receiver test, by the way, is the challenge for most of you, of our audience. So thank you so much, and just waiting to see if we have any questions. I don't see anything coming in, David, so just like to thank everybody. It was really, you know, great presentation. Just speeds go faster and faster, and it just gets more and more complex. But it's good to see where everybody's going. So unless there's some questions, so we just wanted to note that we were working with the high-end Tektronix scopes today, but Tektronix has just introduced a new entry-level scope, which is brand new to them and us, and this is the TP2 series MSO, which is introduced today. So if you want to go take a look at that, you can look at the Tektronix website or the ER website, and the model to look for is the MSO 22 and the MSO 24. And I think that's it. Gentlemen, thank you so much for the presentation. It was awesome.
Thank you so much, Steve.
All right, and I think that's going to do it for all of us today. Please make sure you grab the handout of all the slides before you go. This webinar recorded for y'all if you want to come back, and we'll be sending that out as well. So thanks everybody for coming, and appreciate it. Thank you guys.